Hello guys, my name is Hayden Bird, and this is Physics 2 Lab 3 Magnetic Field of a Bar Magnet. You are able to find a link to the GlowScript code in the bio of my video. The purpose of this experiment was to visualize the magnetic field in both GlowScript and the real world in order to determine the magnetic moment at a certain point. The problem given to us was which of these statements describe what we observe, and the one that I found to be the closest is as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. This is because distance is an underlying factor in both equations, and as you get closer to a magnetic field, its influence on you increases. The physics principles used in this experiment are the magnetic field equations for both a bar and a dipole. The bar is on top and the dipole is on the bottom. A quick review of the results show that the average magnetic moment was roughly 1.828 am squared, and the average distance was 27 centimeters, and the value of n to be found as roughly 4.0467. Using the separate equations allows us to calculate the magnetic moment for both dipoles and a bar, not to be confused with the electric field. And below you can see images of the setup for each of them. I predict that the magnetic field would increase as the magnetometer gets closer to the magnet because distance is a dependent variable in both equations. Having a closer distance should increase the influence of the magnetic fields. And on the right, you can find the materials needed to use this experiment. The system is identified as the smart field, the tape, and the magnetic fields. This includes the magnet and the magnetometer. And the surrounding is the atmosphere, and the smartphone and tape are placed in. This includes the magnetic fields of other devices and Earth itself. Here are the following defined initial conditions that I used for this experiment. The following is a display of an Excel sheet that contains both raw and processed data points for the relationship between distance and magnetic field. As you can see, as distance decreases, the x component of the magnetic field increases, giving us a line of best fit of y equals negative 3.46x minus 14.774. This contains both the on-axis and off-axis fields that were used in this experiment. However, data is not without its error. Possible sources of error include, on the systematic side at least, other nearby electronic devices emitting their own magnetic field, which could have skewed the magnetic fields of either the dipole or bar being measured. Random sources of error include potential human error in measuring dimensions of tape or distance of attraction. This also includes holding up the smartphone and measuring an incorrect value, or moving the smartphone while measuring. This is the first part of my GlowScript code. As you can see, the constants were taken from my initial conditions. And on the right, you can see the function for magnetic field. This allowed me to create the magnetic field assuming a var charge when giving set constants. I had to calculate both r magnitude and r hat and plug it into the Biot-Savart equation in order to find the magnetic field. This is the second part of my code. I would like to go into detail about creating observations locations, as it allows us to observe the charges from a variety of different locations, and arrows allows us to visualize a magnetic field to understand the direction of forces. As you can see, we had to visualize the magnetic field roughly 45 degrees off of the y-axis, which allowed us to create a vector for the perpendicular distance. As to what that actual model looks like, you can find that on the right. You can see that the model is akin to the visualization of the magnetic field. Of course, for this to happen, we had to neglect certain forces such as the tape's own magnetic field, as well as any other forces or magnets that may or may not exist in my smartphone, as well as air resistance. While I was correct in my prediction that the x component would increase as distance is a known factor in both equations, I did not expect to have so many outside factors impacting the experiment. For example, the certain magnetic fields of a nearby Alexa device or a desktop, or even the Earth's magnetic field itself. There was a lot of different outside factors that could have played a potential part in skewing or affecting the magnetic fields measured in this experiment. When asked if I did not orient the magnetic field along the y-axis, the answer would be that the magnetic field would also exist in multiple directions besides the y-axis. This can include various directions along both the x, y, and z axis, and would have to measure in multiple directions. Therefore, it would not be as easy to assume a certain value when measuring by a smartphone. This distance would also increase because for a general part, it would be further away from the origin because we would have to be dealing with multiple x, y, and z components, whereas opposed to just one. As a result, the magnetic field may have decreased because as something becomes further away from the magnetic field, its influence also decreases. If I were to stick two identical magnets together end to end, there would be a repelling force as like charges repel, creating a completely different dipole field. I would feel at certain points the magnetic field would be zero because of the theory that certain points would perfectly cancel each other out along some existence in the x, y, or z axis. You would also have to subtract one force's influence from another when calculating. As a result, you would find that the magnetic field would generally have less of a value when comparing to measuring just one magnet on its own. Thank you for watching. Please be sure to like, share, and subscribe. Thank you.